Now, I want to start off with the oscillator section. The oscillator can be found over here, and if you look at the routing matrix, it is the very first module in a series of modules, essentially. The reason for this is because the oscillator is what generates the initial sound of a synthesizer. Think of this example for a second. If you're a guitarist, you may have multiple guitar pedals which affect the way the guitar sounds, but it is the guitar instrument that generates the actual sound. And then that goes through a series of modules or effects, and it gets changed in some way. The oscillator is our guitar. It is what generates the sound. Now, depending on the waveform that you select on the oscillator, you're going to get a different sound. Let me explain what this actually means. So, the most basic waveform possible is known as a sine wave. This right here. It's kind of like a curvy wave. The reason why this is the most basic waveform is because it only generates one single frequency. So if I play a note quickly, I want you to have a look at the frequency spectrum over here, and we're only getting one single frequency. I'm just going to turn the volume down a bit. There you go. Nothing else. Now, every single sound in existence is made up of a combination of frequencies. So it could be said that every sound is simply multiple sine waves put together, and in theory this would be true. But each sine wave would need to have a different amplitude and specific pitches and so on. So it'd be very complex to put together loads of different sine waves to generate a sound. Therefore, we've got different waveforms. If I go from a sine to a triangle wave, we're going to get, again, a different set of harmonics. This time, not just one single frequency, but more. See, now we have additional frequencies. Let me put this to the side, and I will be changing the waveform with the wavetable position slider. This is what this is. I'm going to be changing this as I play a note so you can see the different harmonics being generated. So sine wave is the purest sound because it generates nothing but one single harmonic. Triangle is a little bit brighter. It generates additional harmonics. Saw, or otherwise known as sawtooth, which is this, is a very bright waveform. It generates a lot of harmonic content. And finally, square wave is kind of in between triangle and saw. It generates a lot of harmonics as well, but not as many as sawtooth. And a square wave can also be known as a pulse wave. So if you're using a different synthesizer and you see the name pulse, that's the same as a square wave. Now, with a synthesizer such as Massive X, they give you literally hundreds of waveforms to choose from in the form of wavetables. Now, each one of these is known as a wavetable because it contains loads of different waveforms within it. And you can pick and choose which waveform you're using by moving this from left to right. This is known as the wavetable position control. And you can see the waveform changing, and each one of these is going to generate a different sound. It would literally take a year to go through every single wavetable and every single waveform and actually learn what they all sound like. So we're going to cover the basic waveforms, sine, triangle, square, and saw, because these are the ones most commonly found in all synthesizers. These are the waveforms that were generated in analog synths, and therefore they've been brought over to pretty much all software synthesizers such as Massive X, Serum, Sylenth. I could name quite a few. So let's say we want to make a basic bass sound. Well, first of all, we need an oscillator or a waveform that will generate quite a powerful low frequency because bass is low frequencies. But we also need a waveform that will generate some high frequency so that the bass can be heard through a multitude of other instruments that may mask the bass. In addition, think about this. If your bass is made purely of a sine wave and you're simply playing a low frequency such as this, if you're wearing good headphones or you're listening to this in good speakers, you'll hear the bass. However, on a small phone or laptop speakers or weak earphones, the bass is going to disappear. That's why when you're making a bass, you want to have some additional harmonics. So something that most producers do for a nice sort of tech house / house bass is use a square wave, but because it's very bright, we turn on a filter and take away the high frequencies. So we're left with the fundamental that would be equivalent to the sine wave, but we still have some upper harmonics to give a little bit of brightness to the bass. Let me explain how this works. The oscillator generates the sound. It is here in the routing matrix. It's routed to A. A allows you to add effects to the sound at this point in the signal chain, such as distortion, bit crushing, and various other effects we'll go through. Right now it's turned off, so it's kind of skipping through A and going to F. F is the filter module. F allows us to select low-pass filters, as well as high-pass filters, bandpass filters, and even filters that kind of distort the sound themselves in some way. And using this main filter control here, frequency control, this is also known as the cutoff in other synthesizers, you can start to take away part of the sound. A low-pass filter simply cuts the high frequencies and lets the lows pass, hence the name. So if I move this to the left, it's going to start taking away high frequencies and leaving the lows present. Therefore, we can get a bright waveform in our oscillator and remove some of the high frequencies and be left with a fairly deep sound. Okay, back to the oscillators. Now, within the oscillator, there's a few more controls. Let me just go through all of them so you know what they all do. So we've got the volume for the oscillator, as well as turning them off and on. You can also turn them off and on from the routing matrix by right-clicking. In the standard waveform read mode, we've actually got a filter itself. And this is just a standard low-pass filter. So if I deactivate the actual filter module, so we've got the full frequencies of the square wave, I can start to take some of these frequencies down using this filter. You see, it works in a very, very similar way. Now, we've got phase, which we'll get onto in a little while. Here, you can adjust the pitch of the oscillator. So let's say you wanted to turn on oscillator 2, and let's go with a saw, and make this play an octave lower. We can do this, 12 semitones equals 1 octave, and it's playing an octave lower. Now, there are something that Massive X does incredibly well, the wavetable read modes. This can morph the wave that you have selected even more so. Now, the first one I want to talk about is hard sync, because a lot of them, such as mirror and wrap, are modeled after hard sync and give you a very similar effect. Hard syncing is quite simple once you understand it. Imagine we have two oscillators. We'll call this one the slave and this one the master. This is what the technical terms I use are. So slave and master. Now, when I play, we're going to go to a sine wave to keep it simple. When I play a note on my MIDI keyboard, a frequency is produced. Let me also go back to just a pure sine wave. So, when I play a note on my MIDI keyboard, a single frequency is generated. That frequency depends on the note that I'm playing. The higher the note, the higher the pitch or frequency that's generated. What this basically means, so right now I'm playing B2 on my MIDI keyboard. It means that in order to generate the pitch of B2, the waveform needs to oscillate, in this case, 123 or 24 times per second. Now, just so that this fully makes sense to you, I have bounced a pure sine wave out to audio. And I want to explain what a cycle is. So, one cycle, one waveform cycle, is when the waveform goes from its center point here, up, that's positive polarity. So, center point, up, down, and then back to the middle. This is one waveform cycle. So if we want to generate a frequency of 100 hertz, this would have to go up, down, and back to the middle 100 times per second. This is what 100 hertz means. Now, of course, if this oscillates or completes 200 waveform cycles per second, the pitch is going to be double the 100 hertz frequency. I hope this makes sense. So what hard sync does is it slaves an oscillator to another oscillator, so that if the second oscillator is completing a waveform cycle quicker than the first one will force its waveform cycle to restart from the beginning when the master oscillator restarts. So that would basically look something like, let's say this is our slave oscillator, and this is the beginning of the waveform cycle, and it goes up and down and then back to the middle. Well, if the master oscillator was to complete a cycle from here to here, the slave oscillator would restart its cycle again from here, which means from wherever this wave is right now, it would jump back to the middle and restart its cycle. So it might end up looking something like let's say it could be anything like this, kind of like overlapping and starting again from the beginning, even though it hasn't completed a whole cycle. Now, that's just the technical part of it. The resulting sound is kind of like metallic, distorted kind of sounds. Have a listen. And the reason why it sounds as though the pitch is rising as I'm increasing the ratio is because the master oscillator that Massive X generates internally is increasing in pitch, making the original waveform reset its cycle quicker and quicker. Now there's a few different modes within this. Soft just softens the kind of distorted aspect of it a little bit. And grain even more so. So it sounds a little bit softer. And then a few different modes here. That's just basically whether it lets the waveform cycle reset with the same polarity or with inverted polarity. If you're not really sure what this means, don't worry about it. Just test it, listen to the sound, and pick the one that you prefer. And this is the level of the second oscillator, how much it affects the original one, the slave rather. So, have a go with these controls. Get a good feel for what the difference in sound is. Now, we're only using a sine wave. As soon as we go to something like a square, this is going to sound a lot more distorted. Let's go back to hard sync and neutral. And once we get later on in the tutorial and we start modulating this with LFOs and envelopes, you can get some really crazy sounds out of it. Now, like I said, mirror and warp and gorilla they're all kind of modeled after a form of hard sync. So they'll sound very similar. Take off the LFO. This has a filter to kind of filter the upper harmonics. Again, hard, soft, and grain, similar effect. Mirror. Very similar effect. The ones which are different is the bend mode. This is where it compresses and expands part of the waveform cycle. So if you look here, this is an oscilloscope. It will show us what the wave is doing. I'm going to put it on standard mode, on a sine wave. I'm going to zoom in. It's just a normal sine wave, equal on both sides. If I put it on bend mode and I bend it to the right, you see how it's kind of expanded the first half of the cycle and compressed the second half of the cycle. And it's also brighter as a result. We now have something a bit more reminiscent to a sort of very soft saw wave. You see? If I do it the other way around, in this case it sounds very similar because a sine wave is equal on both sides. Once you start to get waveforms which are not equal on both sides, such as a saw, the sounds can be opposite. Because a sawtooth wave is not symmetrical. Have a look. That's what it's doing to the waveform. And yeah, usually it can just make the waveform a little bit brighter or a little bit darker depending on which side you bend it. It's something I don't really use very often just because there are so many wave types to choose from in Massive X. Usually just finding the right one is enough. But if you know the kind of sound you're going for, go ahead and use it, of course. Then you've got Gorilla, which again is kind of based on hard sync, but they haven't released too much information on this because it's unique to Massive X, and I guess they don't want other companies to copy it. Again, you can get some very nice distorted additional harmonics. You can see it's kind of adding extra waveform cycles. But one thing I notice is it keeps the fundamental harmonic the same. This one right here, it's always there regardless of the level. And it's kind of pitch shifting upwards and downwards, all the additional kind of metallic harmonics that it's adding. King, Kang, and Kong, it's kind of like hard, soft, and grain. It just changes the type of aggression a little bit. And this again just changes the harmonics that are added on top. 5, 6, and 1. So 1 is a little bit darker, 6 is a little bit more focused on the upper harmonics. So if you want a darker sound, 1, kind of brighter sound, more aggressive, 2. Now, I want to give you a few examples of what you can do by combining Gorilla with PM1, or otherwise known as phase modulation. And then I'll explain what phase modulation does. So here is Gorilla on Kong on ×1, so we get a kind of deep aggression. And you can even bend the waveform, just like in bend mode, which generates sort of even more tonal control. If I activate PM1 and I turn this up, listen to the effect. Now if I change the pitch of the phase modulation oscillator, really, really aggressive sounds. If I turn the internal phase off, so it's going to use the phase of the phase modulation oscillator, this can control it even more tonally to my ears. Let me explain what the phase oscillator does, and then hopefully you won't only be able to apply it, but you'll understand what's going on. I'm going to go back to standard mode. The phase modulation, what it's doing is it's modulating, in basic terms, the pitch of the main oscillator. So if I use a phase modulator at a very low frequency, so I'm going to turn it to key track, down as many semitones as possible. I want you to see how the pitch is being modulated from left to right. Do you see that if I reduce the amount of modulation? It's doing it so quickly now that you can't really see it. You can kind of see it there. Going back and forth, back and forth. Now, when this happens at a harmonic frequency, so that means a key tracked frequency. So if I play the note C, the phase modulation oscillator is also going to be oscillating at the same frequency of C. It starts to sound harmonically related, but also quite metallic and aggressive. You also don't perceive it as pitch modulation anymore because it's modulating it so quickly. And then if I detune the phase modulation oscillator from the original oscillator, you get even more aggressive sounds. But it sounds best when it makes harmonic sense. So 12 semitones down is the same pitch as the original, but an octave lower. And therefore the harmonics generated are mostly enharmonic. If we go 7 semitones up, again, makes sense. 5, but 2 kind of seems to change the pitch a little. 12, 17, again, doesn't really sound like it's generating the same pitch as the note you're playing. Go, say, 9. Same thing with 9, however, minus 5. Sounds pretty good. So experiment with this. We can also change the waveform that's being used to modulate the pitch of oscillator 1, or the phase. And all of these give you drastically different results. Combine this with hard sync or gorilla. Apply a filter. Modulate the filter. And you get some extremely cool sounds. Change the waveform. Saw wave is a little bit brighter than a square wave, and you can hear that's what happened to the sound. Triangle. A little bit darker than a square wave, and that's also what happened to the sound. Maybe go to a different waveform. Maybe apply some effects. A in the routing matrix, oscillator 1 to A. Go to A, apply a few effects such as distortion, high quality, without, with. And you can get some extremely cool sounds. So that basically covers it for the oscillator section. There is a few more modes, and I recommend you can read the manual. They've got some really quick, simple descriptions on them. Random and jitter just kind of applies a sample and hold. module to the oscillator so that you get some randomization. And to my ears, doesn't really sound that good unless you're creating sound effects. Right? Let me go back to just a basic triangle wave, listen to it. And then random, similar thing. Kind of generates noise. So use it as you will. If you want complete descriptions on them, take a look at the manual online. Very, very short, clear descriptions about the ones that you're probably going to be using the most. I think I've gone through. The final one is formant. Now, formant, pretty much most synths have something like this. It just changes the formants of the waveform. So all the harmonics shifts them up or down, just like if you think of people's voices. People with a higher voice have higher formants than people with a lower voice. You can see them moving up. It retains the pitch, but shifts the formants up or down.